Welcome! In this session, we'll explore the problem number 2151, maximum good people based on statements. We'll break down the problem, analyze the approaches, and uncover the optimal solution. Let's dive in and solve this step by step. In this problem, we are trying to determine the maximum number of good people in a group based on the statements they make about each other. The group is made up of n people, and each person is either categorized as good or bad. Good people always tell the truth, meaning their statements are reliable, while bad people can either tell the truth or lie, making their statements unreliable. The information about these statements is provided as a 2D array called statements, where each entry, statements I, J, represents what person I says about person J. A value of 0 means person I claims that person J is bad, a value of 1 means they claim person J is good, and a value of 2 means that they make no statement about person J. The goal is to find the maximum number of good people that can exist in the group, ensuring that the statements made by all good people are consistent with one another. To achieve this, the output of the problem will be an integer that represents the maximum number of good people in the group. Let's look at an example to understand the problem better. Suppose the input is a statements array where person 0, person 1, and person 2 make statements about each other. If we assume that person 0 and person 1 are good, their statements align and are consistent. For example, person 0 claims that person 1 is good, and person 1 claims that person 0 is good. This mutual agreement validates their statements. In this case, person 2 is bad, so their statement becomes irrelevant as it does not impact the consistency of the good people's claims. In this scenario, the maximum number of good people is 2. Now, let's examine another example where the statements array involves 2 people. Here, if we assume that only person 0 is good, their claim that person 1 is bad is consistent with the setup. Since person 1 is bad, they can make any statement, and it will not affect the consistency of the good person's claims. With this configuration, the maximum number of good people is 1. This shows that the problem revolves around carefully selecting subsets of people to be good while ensuring their statements remain logically consistent. To solve the problem, we make a few key observations. First, because the value of n is relatively small, with a maximum of 15, we can use a brute force approach to test all possible subsets of people as either good or bad. This involves generating all 2 to the power of n combinations of good and bad people. For each subset where certain people are assumed to be good, we verify that their statements are consistent. Specifically, if a good person makes a statement about another individual, that statement must correctly reflect whether the other person is good or bad. Among all valid configurations, we return the maximum number of good people. This ensures that we exhaustively explore all possibilities to find the optimal solution. To tackle this problem, let's first consider the brute force approach. The idea here is to generate all possible combinations of good and bad people for the group of n individuals. Since each person can be either good, represented as 1, or bad, represented as 0, there are 2n possible configurations. For each configuration, we validate whether it satisfies all the statements made by the good people in that configuration. This is based on 2 key observations. Good people always tell the truth, so their statements must align with the configuration, while bad people can either lie or tell the truth, meaning their statements can be ignored. The process involves generating all these configurations, validating each one, and keeping track of the configuration with the maximum number of good people that satisfies the conditions. However, this approach comes with a high computational cost. The time complexity is 2 to the power of n asterisk n squared, where generating the configurations contributes 2 to the power of n, and validating the statements contributes n squared. Additionally, the space complexity is n, to store the current configuration being checked. The brute force approach, while simple and guaranteed to provide the correct answer, is computationally expensive due to its exponential time complexity, making it impractical for large values of n. To address this, we turn to an optimized backtracking approach. Here, instead of blindly generating all configurations, we build valid configurations incrementally. At each step, we decide whether a person is good or bad and validate the configuration dynamically to prune invalid paths early. This relies on the fact that good people's statements must align with the configuration. If a partial assignment leads to contradictions, we can backtrack immediately without exploring further. This process is implemented using a recursive backtracking function that assigns good or bad status to each person. During each step, we validate the statements of the assigned good people. If valid, we proceed to the next person, otherwise, we backtrack. This method significantly reduces redundant computations while still exploring all valid configurations. The worst-case time complexity remains O(2 to the power of n), but pruning reduces the search space significantly for most inputs, and the space complexity is O(n) due to the recursive call stack. The optimized backtracking approach improves efficiency through pruning, which eliminates unnecessary computations. However, it is still exponential in the worst case. To push efficiency further, we can consider using bit masking with optimization. This approach leverages bit masking to represent configurations compactly and validate statements efficiently. Each configuration is represented as a bit mask, where each bit corresponds to whether a person is good or bad. To streamline the process, a pre-computed validation table maps each configuration to whether it satisfies all good people's statements. By representing configurations as integers and using this pre-computed data, we can validate statements in constant time for each configuration. The overall process involves iterating over all bit masks, checking validity using the pre-computed table, and tracking the configuration with the maximum number of good people. The time complexity is O(2 to the power of n*n for validation, and the space complexity is O(2 to the power of n, driven by the pre-computed table. While this method is efficient for validation, its high memory usage makes it less practical for large N. After evaluating the different approaches, the optimized backtracking approach emerges as the best choice due to its balance of simplicity and efficiency. While bit masking offers faster validation, its memory usage grows exponentially, making it impractical for larger values of N. The brute force approach, though straightforward, is computationally infeasible for larger inputs because it lacks any mechanism to eliminate redundant computations. Backtracking, on the other hand, strikes a balance by using pruning to reduce unnecessary computations, significantly improving speed compared to brute force. It also avoids the memory overhead of bit masking, making it scalable for moderate N. However, there are trade-offs. Backtracking is slower than bit masking for small inputs, but its space efficiency makes it a better option for larger inputs. For very large inputs, all approaches struggle due to the exponential growth of the problem's complexity, but backtracking remains the most practical. In conclusion, the optimized backtracking approach provides an effective solution, combining manageable time complexity, reasonable space usage, and ease of implementation, making it the preferred strategy for this problem. To solve this problem, we first need to understand its structure. We are given a group of n individuals, and for each person, we need to classify them as either good or bad. The challenge lies in determining all possible combinations of these classifications and verifying which ones meet the required conditions, such as statements made by the individuals about each other. To systematically explore all possibilities, we can use binary representation. Since each person can only be in one of two states, good or bad, there are a total of 2 raised to the power of n potential configurations. For example, if n equals 3, the configurations are binary strings like 000, 001, 010, and so on, up to 111. This binary representation ensures no possibilities are missed and provides a structured way to iterate through all combinations. Once we have a configuration, we interpret it as the assumed ground truth. For instance, if the configuration is 101, we assume person 1 is good, person 2 is bad, and person 3 is good. This sets the stage for validating these assumptions against the given conditions. Now that we have each configuration, the next step is to validate it. This involves checking if the configuration aligns with the given conditions, such as statements or relationships between individuals. For example, if person I claims that person J is good, we need to check whether this statement holds true under the current configuration. Logical rules play a key role here, as we systematically verify the consistency of all statements. If the configuration satisfies all the conditions, we mark it as valid. To keep track of these valid configurations, we use a data structure like a list or a set. Each valid configuration essentially represents a potential solution to the problem. Finally, after processing all configurations, we output the valid ones. Depending on the requirements, we might also analyze these configurations further to identify patterns or determine the optimal solution. There are several key insights to consider as we dive deeper into the algorithm. First, the number of configurations grows exponentially with n. Because of this, the brute force approach is practical only for smaller values of n, such as 20 or less. Next, the use of binary representation is particularly efficient, as it directly maps to the two possible states for each individual, good or bad. This makes it straightforward to generate and iterate through all configurations. The most critical part of the process, however, is validating the configurations. Efficient validation often requires evaluating statements or relationships, and auxiliary data structures can help here. For instance, an adjacency matrix could represent pairwise relationships, while a dictionary could handle more complex conditions. These structures enable us to manage the logical checks with greater efficiency. Additionally, storing configurations as lists makes it easy to represent and access each possible combination, such as 0, 0, 1, for a group of 3 individuals. To store the valid configurations, we use a set, which ensures that only unique configurations are kept. This is important to avoid duplicates and to streamline the output. When it comes to optimizing the algorithm, a few strategies can significantly improve performance. For example, pruning allows us to skip generating complete configurations if a partial configuration already violates the conditions. This is similar to a backtracking approach, where we stop exploring invalid paths early. Another valuable technique is parallel processing, which allows us to distribute the generation and validation of configurations across multiple threads or processes, especially for larger values of n. Pre-processing is another optimization strategy. By simplifying or restructuring the conditions beforehand, we can reduce the complexity of the validation step during each iteration. These techniques help make the algorithm more scalable and efficient while ensuring that the solution remains correct and comprehensive. This implementation solves LeetCode problem number 2151, maximum good people based on statements, using a brute force approach to evaluate all possible configurations of individuals being good or bad. The maximum good function begins by determining the size of the input matrix, n, which represents the number of people. It defines a helper function is _valid that checks if a given assumption about the goodness of individuals is consistent with their statements. For each person I, if they are assumed to be good, the function validates their statements about others. If a mismatch occurs, e.g., person I says J is bad but J is assumed to be good, the assumption is invalid. The algorithm iterates through all 2n possible combinations of classifications using a bit mask. For each combination, it generates an assumption list where each bit represents whether a person is good, 1, or bad, 0. If the assumption is valid, the number of good people in it is compared with the current maximum, and the maximum is updated if necessary. Finally, the function returns the highest number of good people found among all valid configurations. This exhaustive search ensures correctness but has a time complexity of 2 to the power of n*n squared, which is feasible for small values of n, up to 15, as constrained by the problem. Here, we begin by defining the maximum good method, which takes a 2D array of statements as input. The size of the array, n, represents the number of people making these statements. We initialize max good to 0, which will eventually store the maximum number of good people we can determine. Then, we use a loop to iterate through all possible combinations of assumptions about who might be good or bad. This is done using a binary mask, where each bit represents whether a person is assumed to be good or not. For instance, if mask in1 evaluates to 1, we assume person I is good, otherwise, they are bad. These assumptions are stored in an array. Next, we call the isValidHelper method to verify if the current assumption is consistent with the given statements. If the assumption is valid, we calculate the number of good people in this combination using the countGood method and update maxGood to hold the maximum value found so far. Finally, the method returns maxGood as the result. The helper method isValid checks if the current assumption aligns with the given statements. For each person assumed to be good, indicated by a value of 1 in the assumption array, we validate their statements about all other people. If person I claims that person J is bad, represented by a 0 in statements I, J, but our assumption marks J as good, there's a contradiction, so the assumption is invalid. Similarly, if person I claims that person J is good, represented by a 1 in statements I, J, but our assumption marks J as bad, that's also inconsistent, and we return false. If no contradictions are found, the assumption is valid, and we return true. The countGood method then counts the total number of good people in the assumption by summing up the values in the array, where each one contributes to the count. This count helps determine the maximum number of good people for valid assumptions. To solve this problem, we start by looking at the example input where the statements are given as a 2 by 2 matrix. Each row represents what a person says about others. 2 means no statement, 1 means the person is good, and 0 means the person is bad. Here, n is 2, meaning there are 2 people, and we initialize max_good to 0 to keep track of the maximum number of good people we can identify. Next, we generate all possible assumptions about who could be good and bad. Since there are 2 people, there are 2 squared or 4 possible combinations. Each combination is represented as a binary mask, where a 1 at position I means person I is good, and a 0 means they are bad. For example, the mask 2000 foot corresponds to the assumption 0, 0, where no one is good, while the mask 11 corresponds to the assumption 1, 1, where both people are good. This setup allows us to systematically evaluate each possibility and determine which assumptions are valid based on the given statements. Now, we validate each possible assumption to see if it aligns with the given statements. Starting with mask equals 0, which assumes 0, 0, no one is good, so there are no statements to check, making this assumption valid. The total number of good people is 0, so max_good remains 0. Next, for mask equals 1, the assumption is 1, 0, meaning person 0 is good and person 1 is bad. Person 0 statement says person 1 is good, which contradicts the assumption, so this case is invalid. For mask equals 2, the assumption 0, 1 means person 1 is good and person 0 is bad. Person 1's statement says person 0 is bad, which matches the assumption, making this case valid. The total number of good people is now 1, so we update max_good to 1. Finally, for mask equals 3, the assumption 1, 1 means both people are good. Person 0 says person 1 is good, which aligns, but person 1 says person 0 is bad, creating a contradiction. This case is invalid. After evaluating all cases, we find that the maximum number of good people is 1. In the next example, we consider a larger input with 3 people, where the statements are given as a 3 by 3 matrix. Each row represents what a person says about all 3 people. 2 means no statement, 1 means the person is good, and 0 means the person is bad. Here, n is 3, and we initialize max_good to 0. With 3 people, there are 2 cubed or 8 possible combinations of good and bad assumptions, each represented as a binary mask. We start by evaluating mask equals 0, which assumes 0, 0, 0. Since no one is good, there are no statements to validate, making this assumption valid. The total number of good people is 0, so max_good remains 0. For the final case, we evaluate mask equals 7, which assumes 1, 1, 1, meaning all 3 people are good. We check the statements, person 0 says person 1 is good and person 2 is bad. However, this contradicts the assumption that all are good, so this case is invalid. Similarly, we validate each of the remaining masks, systematically checking for contradictions and counting the number of good people in valid cases. After evaluating all possibilities, we find that the maximum number of good people is 2, achieved with a configuration such as 1, 0, 1, where persons 0 and 2 are good. The final results are, for example 1, the maximum number of good people is 1, and for example 2, it is 2. In this problem, we use a brute force approach to explore all possible combinations of good and bad people, and then validate each combination against the given statements. Let's first analyze how we generate these combinations. With n people, each person can either be good, represented as 1, or bad, represented as 0. This means there are 2 n possible combinations of assumptions. To generate each combination, we use bitwise operations to form an assumption array of size n, which requires n time per combination. Therefore, generating all combinations takes a total of n*2 to the power of n time. Next, each assumption is validated. For a single assumption, we check whether it satisfies the statements made by all n people. Validating involves iterating over all n people, and for each person, examining their statements about all other n people. This results in O, n squared, work for each assumption. Together, these steps lay the foundation for our total complexity analysis. Now, combining the two steps, we need to validate all 2n assumptions, and each validation takes O, n squared, time. This results in a total time complexity of O, n times 2 to the power of n times n squared, which simplifies to O, n squared asterisk 2 to the power of n. This exponential time complexity arises because we explore every possible combination of good and bad people and validate each one. Turning to space complexity, the memory usage can be broken into a few components. First, the assumption array we generate for each combination has n elements, using O, n, space. Importantly, this array is regenerated for each combination and does not persist beyond the current iteration. Furthermore, since the solution does not use recursion or additional data structures that grow with input size, there is no extra memory overhead from the algorithm itself. Additionally, we must consider the storage required for the input. The statements matrix is given as an nxn2d array, which requires O, n squared, space to store. When combining all these factors, the space complexity is dominated by the statements matrix, so the overall space complexity is O, n squared. Comparing this solution to a naive brute force approach, both methods involve exploring all 2n combinations of good and bad people. However, the given solution optimizes the process by efficiently validating combinations through the is_valid function. While the time complexity remains exponential, the optimized validation ensures that redundant computations are minimized. This makes the approach as efficient as possible given the constraints of the problem. Now let's break down the time complexity further across best, average, and worst cases. Since all 2n combinations must be checked regardless of the input, the best case time complexity is still O, n squared asterisk 2 to the power of n. Similarly, the worst case complexity remains the same because the algorithm always explores all combinations. For the average case, there is no significant difference from the worst case, as every combination is considered systematically. Mathematically, the 2n term arises because there are 2n ways to classify each of the n people as good or bad. The n-2 term comes from the nested loops in the is_valid function, where every person's statements about every other person are validated. These two components multiply, resulting in the overall time complexity of O, n squared asterisk 2 to the power of n. While the solution is computationally expensive due to exponential growth, it is the most direct and feasible approach for solving this type of exhaustive validation problem. When solving this problem, there are several common mistakes that can trip you up. First, it's important not to ignore the constraints provided in the problem. For instance, in edge cases where n equals 0 or 1, the solution might be straightforward and not require complex computation. Overlooking these can lead to unnecessary runtime errors. Next, avoid inefficient brute force implementations. If you generate all 2 to the power of n combinations without eliminating invalid configurations, you'll waste a lot of time on unnecessary computations. Instead, think about how you can reduce the search space by taking advantage of the problem's constraints. Another mistake is failing to validate intermediate results. Many solutions require that each configuration satisfies the given conditions, such as specific relationships or rules. Skipping this step can lead to incorrect results. Lastly, always look for optimization opportunities. Identifying patterns like symmetry, using memoization, or applying dynamic programming can help you craft a much more efficient solution. By focusing on these aspects, you can avoid common pitfalls and improve the quality of your solution. Another common mistake is misinterpreting the problem requirements. A good example is misunderstanding the distinction between good and bad configurations or how the output should be defined, whether it's the count of valid configurations or the configurations themselves. Carefully reading and fully understanding the problem statement is essential here. Now, when it comes to interviews, there are a few strategies that can make a big difference. Recognizing patterns is crucial. Many problems in this category are built on structures like subsets, graph traversal, or constraint satisfaction. Identifying these early can guide your approach. Also, it helps to break down complexity. Start with a brute force solution to establish a baseline, then outline its limitations and explain how optimizations like backtracking or dynamic programming address these issues. Another key point is to communicate trade-offs. If you're considering different approaches, be sure to discuss how they compare in terms of time complexity, space usage, and implementation complexity. Finally, always test edge cases like empty input, single element input, or the problem's maximum constraints. This shows interviewers that you're thorough and methodical in your approach. This problem also has connections to several related problems on LeetCode. For example, LeetCode 78, which involves generating all subsets of a given set, is conceptually similar because it requires exploring all possible configurations. Another variation is LeetCode 90, which deals with subsets but includes duplicates, requiring additional filtering to ensure only unique subsets are included. Then there's LeetCode 473, Matchsticks to Square, which is a backtracking problem that focuses on partitioning elements into groups that satisfy specific conditions. This requires carefully validating each grouping. Lastly, LeetCode 131, Palindrome Partitioning, is another relevant problem. It emphasizes recursive exploration of valid partitions, highlighting the need to validate intermediate results. Studying these related problems can provide valuable insights into solving this challenge, as they share similar principles and techniques. There are several alternative approaches to solving this problem, each with its own advantages and disadvantages. Backtracking is a common choice because it systematically explores all configurations while pruning invalid ones early, which helps reduce the search space. However, it still has exponential time complexity for larger inputs. Dynamic programming is another option, offering significant performance improvements by memoizing intermediate results and avoiding redundant calculations. The trade-off here is that it requires careful design of the state representation and typically uses more memory. Greedy algorithms can also be considered for problems with simpler, more straightforward constraints. They're fast and easy to implement but often fall short for scenarios that require exhaustive exploration. Finally, graph-based approaches are particularly useful for problems involving dependencies or relationships between elements. These methods leverage graph traversal algorithms to find solutions efficiently, though they require a solid understanding of graphs and their properties. Each of these approaches has its place, and the best choice depends on the specific characteristics of the problem you're tackling. Thank you for joining. We've reviewed the problem, discussed the brute force approach, and highlighted key takeaways. Remember, practice makes perfect. Keep solving problems and refining your skills. Don't forget to like and subscribe for more coding tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!